Hey everyone, welcome to my talk. So today I'm going to talk about my experience building a Kubernetes terminal dashboard in Rust. So let's begin. Short introduction. My name is Deepukesh Shashidharan. I'm the co-lead of JHipster. I also created a nifty dashboard called KDash for Kubernetes. I'm an open source aficionado and a polyglot developer. I primarily work with Java, Rust, JavaScript, and Go. I work as a developer advocate at Okta with a focus on DevOps. I also publish frequently about languages and tech on my blog. You can find it on deepu.tech. Please do follow me on Twitter if you are interested in my content. I have written a book about JHipster. So if you like this talk, you might like the book as well. So please do check it out. So, okay. So, what is KDash? So, first, let me introduce you to KDash. So, KDash is a simple terminal dashboard for Kubernetes. So, it provides common resource views, node metrics, logs, and so on. Let me quickly give you a demo. I'm going to share my screen. I'm on a single monitor here, so this is a bit more weirder than usual for me to, screen share and stuff.
Yes, so everything is great. I already shared your screen, so we see perfectly.
Yeah, I'm going to switch to a different view because I'm on a single screen, so I'll take care of it. No worries. So share screen. Okay. So I'm going to fire up KDash, and this is the. I'm just going to make sure that it is visible. Yes, it's visible. Yeah, so this is KDash, and as you can see, we have a lot of common resource views that is commonly used. We have pod services, nodes, config maps, and so on. We also have more resource views under a submenu, the lesser used ones. You can see some bit of context info. You can see namespaces on the top. You can go in and you can select namespaces around. You can filter by different namespaces. You can go in and select all namespaces if you want. You get a little bit of context info of what cluster you're running, the total CPU and memory being used, and etc. You also get a little bit of info about all the CLIs that is found on your system, like kubectl client, the server, Docker, and so on. And that's the main context view. And then we also have all context screen where you can switch between contexts. So the context switch would be in memory, so it won't affect your global kubectl context or anything. So if you switch a context in KDash, that's only for that particular session. So when you restart KDash, it will fall back to whatever was your default context in your kubectl configuration. And finally, we have a utilization screen, which is one of my favorite. So it gives you an overview of resource usage on your cluster, and you can switch around the grouping. For example, you can group by namespace or by resource type. You can go by node. You can go by specific resources and etc. So this is by resource view, and this is by resource, node, namespace, and like grouped by resource, then node, namespace, and then pod. And this is grouped by resource, node, and namespace, and finally by resource and node. So you can switch around with all those views, and you can come back to the context and everything. So that's about what KDash does. It's quite simple. So I'm going to switch back to my other view. Share again. Sorry about the back and forth with shares and stuff. A bit, yeah. I'm currently on vacation, so I don't have all my setup with me. sorry about that. And we went through this. So the thing that I wanted to talk about in this session, mainly, was why did I build another Kubernetes dashboard? Because we don't have any. We have an abundance of Kubernetes dashboards out there. There are excellent solutions out there. There is the awesome KNNS project, for example, which is quite similar to KDash. That one is written in Go. It offers full CRUD operations on the Kubernetes resources, whereas KDash only offers view for now, of resources for now. And KDash was definitely inspired by KNNS. So when I started learning Rust, almost a year ago, I wanted to build something more than hello worlds and to-do apps. So I decided to build something useful with it. And after pondering over many ideas, trying few different things, and I was working with Kubernetes a lot at that time, and I was using KNNS, and I thought, hey, there are some things that I like KNNS, but there are some things that I would probably do differently, or there are some things that I would want to have differently. So why not just build another dashboard and for Kubernetes, but in Rust, instead of Go, in Rust. So that was the initial idea. So mainly it was for educational purposes. So I started building, and I had few goals. So in terms of UX and navigation, I want KDash to be much more simpler. I wanted it to be simpler to navigate. I wanted it to be zero like stupid easy to navigate and go around. I wanted like keyboard shortcuts like splashed over everywhere, so that you don't have to remember anything. I wanted it to the navigation to be natural, like how you do in any other pages. Like, for example, I wanted arrow keys to work for resources. I wanted tabs to cycle through pages and all those things. So almost like in a browser. So I wanted that as a goal. So that was the primary goal, like ease of navigation, good user experience, and simpler, overall simpler. So that was the main goal. Of course, building that in Rust as an added bonus, without actually having that as a goal, it also is really fast and memory efficient. Even though that wasn't my initial goal at all, but it's extremely memory efficient and fast. Now the question that might be on your mind is, why Rust and why not Golang? Because for Kubernetes especially, Golang has a great ecosystem. Most of the tools in the ecosystem, including kubectl and Kubernetes itself, is written in Go. And Helm is written in Go. There are so much stuff in Go. The ecosystem is great. There's so many libraries. So why didn't I go with Go? Why did I chose Rust for it? And honestly, Go is an excellent language for these purposes, and there is no reason to choose Rust over Go for this particular project. Since this is a user space project, so Go would give you almost as good as performance as Rust, though not as good as Rust, but almost there. You won't be able to tell the difference that easily. The real reason I chose Rust is because I was fascinated with it, and I believe it is one of the greatest modern programming language. So I really wanted to put it into actual use and prove that whatever you can do in Go in Kubernetes user space can be done in Rust as well, as probably even easier to do in Rust, because in Go, after a particular point when the project grows, there is so much boilerplate. If you look at the source code of a similar dashboard like KNS, for example, if you look at the source code, there is so much source code there. And if you rewrite that project into Rust, you can cut down the source code by like 1/3. Or even more, because there is so much stuff that you can do in Rust, which makes code reusability much more easier because of the generics and all those things, macros. It makes it much more easier to write reusable code. And project like these, there is a lot of repetition going over, and because of Go's inherent lack of generics and the other stuff that I don't like in Go, for example, like the overuse of the error handling or whatever, all that makes too much code, whereas Rust cuts that down and makes it much more simpler. If you look at the source code of KDash, you'll see that it's much simpler. It's much simpler. It's easy to reason about, and there is a lot of generic stuff that is reused everywhere. So I also believe that Rust is an ideal candidate along with Go for building Kubernetes ecosystem, and the best choice for use cases like proxies, WebAssembly workloads, and performance sensitive tools and applications. The Linkerd proxy is already built using Rust, and there are many more projects using Rust due to its advantages. And if you are in the Kubernetes space, it's a language you should be familiar with and consider depending on the use case at hand. So I would let's take a deep dive into Rust and see why it is unique and why I think it is important. And even though I didn't start out with that as a goal, once I used it to build this, I realized how much more efficient it is to build project like these in Rust. Though there might be a little bit of steep learning curve, but in my opinion, the steep learning curve is worth the final results. So let's see why Rust is important. So for those not familiar, Rust is a high-level multi-paradigm language. It's ideal for functional and imperative programming. So it has a very modern and, in my opinion, one of the best tooling for a programming language. Like I have worked with a dozen programming languages, and so far nothing has come close to Rust's tooling and the Rust community. So it's hands down the best, and no wonder it's the most loved programming language 6 years in a row for the in the Stack Overflow survey. Its advantages and flexibility has also made it suitable for all sort of use cases, because it was originally intended as a systems programming language. But today, people are finding more and more use cases for Rust, like WebAssembly, for example. Nobody thought you could do WebAssembly on Kubernetes, and it is a possibility now. So maybe sometime in the future we might be going containerless. We might not be needing containers anymore. And I think one of the founders of Docker said that if there was WebAssembly when they were coming up with Docker, they probably would have just used WebAssembly instead of building Docker. So that's how important WebAssembly is, and Rust is one of the best languages to work with WebAssembly. So Rust has gone beyond the systems programming domain and has found its way into WebAssembly, that is client-side programming, general purpose web application, microservices, and so on. So so what's so special about Rust? So Rust throws around some buzzwords in its docs, but they're not just marketing buzz. They actually mean it with full sincerity, and they actually matter a lot. The memory management in Rust is what makes it special, in my opinion. The ownership and borrowing mechanism makes it one of the most memory efficient languages, while avoiding pitfalls that comes with manual memory management and garbage collection. It has memory efficiency and speed comparable to C, C++, and memory safety better than that of garbage collected languages like Java and Go. The safety guarantee is another important factor. So Rust is memory safe, null safe, type safe, and thread safe by design. So you would have to, go out of your way to break those guarantees using the unsafe keyword. So by default, whatever you write would be safe, and Rust guarantees that. You'd have to really try hard to write unsafe code. So you may ask, aren't most high-level languages memory safe? And the answer would be sort of. Of course, this is without counting C, C++ as high-level languages, as they are inherently unsafe. Even supposedly memory safe high-level languages like Java, Golang, and C# sometimes suffer from occasional memory leaks, overflow errors, and these kind of things. Whereas and they don't offer the performance of Rust. Since they all use garbage collection or reference counting, which adds certain overhead and affects performance. So Rust ensures memory safety at compile time using its innovative ownership mechanism and the borrow checker built into the compiler. And the compiler just does not allow memory unsafe code unless it's explicitly marked as unsafe in an unsafe block or an unsafe function. The static compile time analysis eliminates many types of memory bug that's common. That's common with C, C++, and stuff like that. So actually, I have another talk coming up in FOSDEM next week, where I'm going to talk about why safety matters in programming, and why a language like Rust is the ideal way to ensure that we have a safer ecosystem and like less vulnerabilities to worry about and stuff like that. So I'm not going to go into dive deep into these aspects here. But just to wrap up, so imagine a world without CVEs caused by memory safety issues that's plaguing our industry due to human error while using C++. Because more than 70% of all CVEs issued across Microsoft, like Windows, Apple, like Mac OS, Android, Linux, iOS, Chrome, whatever you take, more than 70% of CVEs are memory safety issues. So using a language like Rust can get rid of that entire class of errors. So imagine how our industry would be, how much how much developer time we would save, how much money and resources we would save. So there is no concept of null, at the language level in Rust. Instead, Rust provides the option enum, which can be used to mark the presence or absence of a value, making the resulting code null safe and much easier to deal with. And you will never encounter null pointer exceptions in Rust, unlike in Java or even Go, JavaScript. So you wouldn't have to deal with those kind of things. And Rust is statically typed and guarantees type safety by strict compile time checks. And by guaranteeing memory safety, it kind of guarantees type safety. So they kind of help each other. This is not special, as most modern languages are statically typed, and this is not something unique to Rust. Rust also allows some level of dynamic typing with a dyne keyword and any type when required, but the powerful type inference and compiler ensures type safety even when you are using these dynamic typing. And finally, Rust guarantees thread safety using similar concept it uses for memory safety, along with providing standard library features like channels, mutex, and ARC. So the compiler makes it impossible to cause accidental data erase from a shared state. This makes us confident to focus on code and let the compiler worry about shared data between the threads. Later, I'll talk a little bit more about the architecture of KDash, because it is extremely multi-threaded, asynchronous, and there's a lot of threading and shared data going on. And so far, I haven't had any issues that is related to data arrays or whatever. And honestly, I after a while, I stopped caring about those kind of things, because I was so confident in the language that I was like, okay, I can do whatever I want, and as long as it compiles, it's not going to cause any issues. So that's the confidence you get. So if it compiles, it's going to work. Of course, I mean, your app might crash if you have if you have done something stupid in the code. Like, for example, KDash, I found a issue in KDash where the app was crashing with a Stack Overflow, because there was an infinite loop, which was my fault. Right? So there was something that I did causing an infinite loop, and of course the app will crash. Those are what do you call, like, those are predictable issues. Those are not undefined behavior. And the thing is, what you can be confident about is you will not have undefined behaviors like data races or memory leaks or buffer overflows and stuff like that. So but these are all the important features of Rust. Like, these are the features that most people talk about. These are the features that even Rust advertisers, and these are like the main attraction of Rust. But personally, my most favorite feature of Rust is hands down the zero cost abstractions. So I can't stress enough how cool this is, especially if you are doing a lot of functional style programming. And if you're a developer using a high level language like Python, Java, or Go, there is something that you may not be consciously thinking about. So while writing those cool layers of abstractions that impresses your colleagues, every layer of abstraction adds additional instructions and affects performance. In most cases, it might not be noticeable, but that additional performance overhead is there, and they add up. So the more abstractions you write, the more that cost will add up. We all know that imperative code is the most performant code, right, compared to functional style code. And that's due to the same reason. And that's why you can hand code more performant code in these languages. Now, some languages have compilers that are smart enough to convert some of those abstractions to more performant bytecode, but only languages like Rust and C++ offer zero-cost abstractions, which means you can write the code in whatever style and with whatever abstractions or how many ever abstractions without having to worry about performance cost, as the compiler will always generate the most performant bytecode possible, meaning you cannot hand code it any better than what what the compiler has done. For example, you can choose to create or use any number of abstractions to structure your program, like layers and layers of functions, like inheritance or whatever. You could use loops or iterators as you wish. You could do functional programming or imperative programming, and the result remains the same. None of this would affect the performance of your code. You can be quite confident about that. The compiler will produce the best possible implementation of the machine code for a particular use case, regardless of the flavor of code you chose to write. And Rust, for example, comes out of the box. There are so many zero cost abstractions built in, like ownership and borrowing. They are zero cost abstractions. There is no performance overhead because of them. Iterators and closure APIs, there is no performance overhead in using them. In fact, using iterators and closure APIs, like they perform slightly better than your hand coded for loops or whatever. Async await and futures, they are zero cost abstractions. Unsafe code and module boundaries, these are also zero cost abstractions. This is a small sample, like a small illustration using Java and Rust. So on the left hand side, you see a Java code, and on the right hand side, you see Rust code, and they are similar functions. So there is a factorial function. So the first one is using traditional loops. The second method in both are using recursion, and the third one is using inbuilt iterators, right? And if you look above the method, there is a comment with some numbers, and you can see in the Java version, as your abstraction increases, the performance also decreases. So using the one with the least abstraction, which is using for loops, has something like 10 nanoseconds per operations. And if you do the same thing with recursion, suddenly it becomes 20 nanoseconds per operation. So you are doubling the performance cost. And if you do the same using inbuilt iterators, it increases it further by 23. It becomes 23 nanoseconds per operation. So that's like, and it may not be noticeable because we are talking about nanoseconds, right? But imagine if you're writing an extremely performance sensitive application, then all these adds up. And this is just simple factorial. So imagine when you're writing production code with so much abstractions and recursions or whatever. So they're all going to add up a cost. And if you are writing code in not code in languages which is not Rust or C++, then probably, and if you're thinking about performance tuning, then this is one area you could look at abstractions. And if you look at the Rust version on the right hand side, you can see that all three versions have almost similar, like they are almost like 8 nanoseconds per operations, first two, and using the inbuilt abstractions like iterator is actually even better, because it gives you like 6 nanoseconds per operation, because there are some internal the inbuilt in abstractions, they have some tuning inside which you may not be writing in your handwritten code, like boundary checks and stuff, so they make the performance even better. So Rust is also immutable by default, and mutations have to be declared explicitly. This, along with the ability to pass by value or reference, makes it super easy to write functional code without any side effects. So all those out there, fans of functional programming, so Rust is the ideal language for you, because you don't have to worry about abstractions, and you can go super functional and full-blown functional code without having to worry about a lot of these things. Rust also has excellent support for pattern matching, and it's heavily used in Rust style guides and in Rust samples and in Rust docs. So it's default way of handling error and handling optionals and results and stuff like that. Rust also has advanced generics and traits with type aliasing and type inference support. Though generics could easily become complex when combined with lifetimes and stuff, but Rust is extremely flexible when it comes to generics and traits. There is also support for metaprogramming using macros. So Rust supports both declarative macros and procedural macros, and macros can be used like annotations or like attributes or like functions. A lot of built-in functions like print line or format, they're all macros. So in Rust, you can use macros to write reusable code without having to depend on generics, because when it is compiled, all those macros will be expanded into actual code. So that doesn't mean that Rust is a silver bullet, because there are some downsides as well. There are issues like steep learning curve, which is the biggest issue people have with Rust, because you would have to throw away your previous assumptions of how to program and everything because of the ownership and borrow checker. You would have to learn that, and that initial part of learning how Rust memory management works is a bit steep, because you will constantly be fighting the compiler to make your code compile because of ownership errors that it will throw, because of the way that you have used to in other languages. You might be writing code that is not memory safe here, and the compiler will shout at you. Even though there are these complexities, it's the closest thing to a silver bullet, in my opinion. That doesn't mean that I'll start using Rust for everything, right? I still enjoy being polyglot, and I'm still invested in Java, JavaScript, and Go, among others. But if there are use cases that require speed and or concurrency, or building system tools or CLIs and stuff, WebAssembly or stuff like that, then Rust will be my first preference. Maybe Go will take a backseat, because if I can do something in either Rust or Go, then personally I will go with Rust. But of course, there could be teams who are more comfortable in Go. Then there is no harm in going with Go in those cases. So in my opinion, Rust can be the ideal general purpose language once the ecosystem matures. The only problem, I think I'm missing somewhere. Okay, it's fine. So the target for high level and low level languages are quite different, and hence, like, the features and goals differ as well. Like, Rust is a high level language, and hence it's human oriented, but it also has performance and efficiency that puts it into close league with low level languages, and more specifically mid level languages like C++. So normally a language would offer a choice between safety, speed, and high-level abstractions. At the very best, you can pick two of those. For example, with Java, C#, and Go, you get safety and high-level abstractions at the cost of runtime overhead, whereas C++ gives you speed and abstractions at the cost of safety. But Rust offers all three, and a good developer experience and a great community as a bonus. And of course, the extremely good tooling. So Rust also scores great in a 2017 research comparing speed, memory efficiency, and energy efficiency of programming languages. And I'm pretty sure that numbers would have only become better. Do note that there has been some criticism from different language community about this research, especially regarding how optimized the code was, etc. That might explain why Rust scored a bit less than Go in memory efficiency, because in real world examples that I have tried and whatever I have done, I had never seen a scenario where Rust memory efficiency was less than that of Go. If anything, there were some, like, the worst was that they were similar, but never I have seen a case where Rust used more memory than Go for a same thing. Of course, there could be edge cases where it happens, but in general. So you won't appreciate Rust unless you spend a few weeks building something in it. The initial steep learning curve could be frustrating or challenging depending on how you see it. But once past that, it's hard not to love it. It's a toddler with superpowers after all. And the tooling, man, the Rust tooling is one of the best. You'd have to try to appreciate it. You'd have to try Rust to appreciate how good the tooling is and the community is. So that's something for you to go try and appreciate. So now let's see a bit more about KDash. So I used a bunch of awesome libraries, and I highly recommend all of them if you're having similar use cases. Some of the more noteworthy ones are TUIRS, extremely great library for building user interfaces and dashboards. And Tokyo, the default standard in Rust for anything event-driven and non-blocking async IO stuff. And of course, if you're working with Kubernetes stuff, then there is an excellent Kubernetes client for Rust as well. And there are a few other stuff with generic libraries that you would use. So the data architecture of KDash it's highly asynchronous and multi-threaded with an event-driven I/O. So I use a single data store for everything. It is shared across multiple threads with the help of Arc and Mutex. The UA is non-blocking as well. So everything that is going on in KDash is asynchronous, and the UA is rendered in one thread. All the network calls are done in another thread. The commands and stuff are run in another thread, and streaming of logs and stuff happens in another. So there is like 4 threads that I use, and all communication between these threads happens through channels, like events sent through channels, and the data is shared between, like the data store is shared between all these threads using Arc and Mutex. And so far I'm yet to encounter any issues because of this, because if I did the same architecture in another language, maybe Go will come close to Rust in terms of ease of use for this kind of architecture. But if I did this in like maybe Java or C#, then I don't know how much issues I would have and how much of synchronizations and stuff I would have to do. But Rust made it super easy to do such a complicated architecture. So there were some challenges when I was building KDash. The most noticeable notable ones were streaming of container logs was something that I struggled with most, especially due to the async multi-threaded architecture and Rust's strict ownership rules. I had to really struggle a bit to figure out how to make it work properly. So log streaming was causing the app to hang. The logs were getting cut off sometimes. There was a little bit of weirdness in the way log streaming is handled by the underlying Kubernetes library. Of course, the solution was to move streaming to a new thread and switching to Tokyo streams so that I could retry on failures. I could provide a timeout. I could cut off a stream and start at that point later on and stuff like that. So Tokyo streams is an excellent library for that. There are still some log streaming quirks because of the underlying library and the way it provides logs, which nothing major, but still there are some quirks that I would have to solve at some point. There was also some issues with freezing UA initially, as I was doing network IO and UA rendering in the same thread initially. So when I started out KDash, it was like single threaded. I only had one thread, and soon I ran into these kind of issues, and then I figured, okay, this is where I have to make use of the advantages that Rust offers. So of course, most of my solutions were switching to different threads and stuff, because it was so easy to do in Rust, and I was so confident that I won't have to deal with all the issues of using this kind of architecture. So it was the safety of Rust was a boon for doing stuff like this, and it was also so much fun. So that's another thing. Finally, I still have an annoyance of having to update a downstream library for rs lib updates, since the library cannot work if there is another dependency that uses a different version. So generally, I create a PR to the library first before updating. So that's a little bit of the dependency management issue because of the way that particular library is built, because it works both as a CLI and as a library. So that's not something that is common in Rust. It's not the common way to Rust. So it's a bit of a workaround. So but it's not a big thing, minor things. So I was talking about the memory efficiency and speed of Rust, right? So I did some tests. So actually, when I run, let me go back to that. So where is it? So okay, yeah. So running all this, it takes less than 8 megabytes of memory, and even running kubectl takes more than that. So running all this and the utilizations and all this, like you can do whatever, keep switching around tabs, load whatever, like doesn't matter. The memory usage, whatever I tried, the memory usage was under 8 megabytes, and the CPU usage was negligible. Even running kubectl get ports uses more memory than KDash. So that's how efficient Rust is in terms of memory and CPU utilization. So,
Tipu, my friend, excuse me for a second. Could you please assess? Oh, it was.
Yeah, that was it.
Almost like
Yeah. Sorry about that. Yeah, that was my
Because-
last.
Yeah. Okay. Because it actually sounded like you can talk about Rust like whole day long. So I guess we already have someone who would help us with the Rust summit, with the Rust conference. So
Of course.
you have another invite for the program community for the Rust.
Thank you.
Uh,
I could also
alrighty
talk
then.
about Go and Java similarly. So I
Alright.
love these languages. So.
Awesome. Thank you for your presentation.